So we saw exact MVA, approximate MVA, and this is convolution gives you even more detailed results compared to the mean value results that you get from MVA and so on. Okay. So last time we saw how to compute the G of NM, right? That is again. Did we do an example for the G of? We did. Did we compute G values for particular system? Right, we did G of 3 2 we computed, right. So we have the table we computed last time. Okay. So now to look at, so now that we compute these this table, right, and then given n, so we know how many combinations are there and so on, right. So now let us look at how to extract some performance metrics with the help of this convolution algorithm. Okay. So last time I briefly gave you one metric, but now let us look at our this metric. So probability So for some particular queue, right, what is the probability that at least j customers in some queue I? So this you can simply enumerate, right, list all possible combinations, right. We have this entire table available, right. So just you can simply manually go through the table and just routinely count it, but we can also do it. So basically this is summation over all the possible combinations of, right, n such that ni is greater than or equal to j, and we know this is our standard formula, right. This is our yi and this, which we can actually figure out maybe in a tutorial. So if you know G of n, then remember that we compute the table the way we looked at it last time, right. You also compute all the other values in the table, right. Your G of n minus j by comma m is also computed in running that algorithm sequentially. So you can simply store all the G values from 1 to n, right, and then you would get your probability of there being greater than or equal to j customers in a given queue is given by this value. So that is one, and if you want to know exactly how many customers are there, what is the probability of exactly j customers in a queue I, so that is simply probability that there are greater than equal to j minus greater than equal to j plus 1, is that correct? So that will give you the probability that q customers exactly equals j. This is again you can do this. So this is yi to the power j, ignore that something there, that is so with just the demand values, the scale demand values and the G table that you are computing, we can get this. Okay. So now Qi, remember Qi? We are doing this the mean value way, right, last time. So this is the expected number of customers in Qi is given that there are n possible customers, this is simply the probability that ni is greater than equal to j. this is another way of defining the expectation, right. The summation of all the CDFs going from 1 to n is also the expected value of that. Then, so if you want to know the probability that there are say j customers in the ith queue and some k customers, or sorry, L customers in the kth queue, that is almost similar to what we saw, yi to the power j, yk to the power L, g of n minus j minus L. So that is for the actual queue lengths, right. So we now need the utilization, the delays and all that stuff, right. So what is the probability that a queue, given qi is not idle? Based on what we know so far, how do you define that probability? What is the probability? So utilization is basically the probability, these are ui, remember, ui is the probability that the queue is not empty. So what is that? Ni is greater than or equal to 1, right. So we already know that. So that is simply yi to the power 1. So this is gn minus 1 by g. So utilization is now derived from this. So then what is the throughput of a device xi? So how do I get the throughput of device? Remember u equals xs, that is our first law, right. Utilization equals throughput into service time. So throughput equals SI is usually known, service time, right, average service time is known, that is a parameter, input parameter. So we know ui, we can compute xi. Then once you know xi, you can always compute, if you know xi and vi, you can compute x, right, but x can also be expressed differently, right. So x is also equal to ui by di, right. Remember ui equals x into di. So ui we have computed here as yi, right, into gn minus 1 by g of n, and what is di equal to? Remember we did yi is actually alpha into di, right. So yi is alpha di divided by di, so it is simply that's it. So now do we have everything to proceed to calculate R? So we need Ri. So what is Ri? Ri is simply Qi by, right, Q equals XR. We have computed Qi from that expression before, we have computed Xi also, right. So therefore Ri is that. Then after that we have, so then you compute R, then you can compute the overall, well, that's pretty much it. We know X, we know R, that is what we normally try to compute. Okay. Questions? So once you compute that table, then everything is sort of just routine calculations. So let us look at the same example that we saw before, same CPU 2 disks example. Okay. So in that example we had computed SCPU to be, or at least it was given to us that this is 0.039. Then VA is given, VB is given, so we can use that. Right, this was what we had last time, and then we computed DCPU as 0.78. And for alpha equals 1 by 0.78, we had computed that YCPU was 1, YA was 3, and YB was 2. So this is what has been given to us, right? So with just this, we can now proceed to get all the Q values, everything. So with the mean value analysis, with this information, could we have, because n has to be given 2, right? So n is given, n is 3, and your number of devices is also 3, right? And yeah, Z, actually in this case we have taken Z to be 0, so there is a slight modification for delay centers. In this particular derivation we are not considering delay centers, there is a small extension, that is all. Okay. Okay. Number of devices is 3, M is 3. There are only 3 queues, CPU, disk A, disk B. Okay. Okay. So then so we were interested in 1, 3, right? We said G of nm, right? So for G of n is basically nothing but G of 1, 3 in this example, right? So from the table, what is G of n, what is G of 2, and so on. This is basically the last column M in the table. Very nice. So we can compute a whole bunch of things. Okay. So what is the probability that there are at least 2 jobs in disk, in the disk A? So tell me, just compute and tell me the answer, then I will write it down. 0.6. So this is YA squared G of n minus 2 G of n. So this is 3 squared, n is 3, therefore this is 6 by 6. So that is how you get the probability of more than 2 jobs in QA. If you refer to the first table that we computed, remember we computed a longer table with all the 10 possible states, right, where the 3 jobs could be in 10 different states. from that table can you find out what P of Na greater than or equal to 2 is? So the table is being computed. Here we do not have to compute the table, because if I have to enumerate the table, that is a fairly substantially large table, right. So if I do not want to do that, then I simply with just the G values, right, I can compute this, because that is order nm, whereas that one to enumerate all the items in the table is n to the power m minus 1. So there are basically, what are the states there? Out of that, how many states will correspond to what we are looking for? Ya greater than or equal to 2. We did not really list this table completely, okay, but there will be 3 states, 3 states which will have this property. So this is one state, this is another state, then there will be one more state. Well, I guess if you have to write it down, there is not much room here, but you can work it out. So that is another way of verifying that what we are computing is actually correct. This table also gives us the same thing, right. If I compute this table, I don't have to go through all the other calculations. I can simply run my right, just run this as an Excel formula and just add up whatever things that I want, but that is what it tries to do. Given n and m, remember this table that we did.
So why only 3 states in last slide?
Why are only 3 possible states? Okay. What are the other states in?
We can have 1 in CPU, 1 in DA, 1 in disk B.
Okay, if I have 1 here, okay, I can have 1, 2 and then 0. Any other combination? I can't have any other combination. There are only 3 jobs, right. So the only other valid combination is this 1, 2, 0. These are the only 3 cases where number of jobs in QA is more than or equal to 2. This is Ya greater than or equal to 2. Okay. In fact, let us look at the table here. So this is 0.2, 0.3 and then 0.1. So that is all. Okay, proceed. Can I? It's already there. Okay, so then if you want, so what is the probability that there is exactly one customer, there is exactly one customer in this queue. So there is Ya by Gn G of minus 2, which is 3 by 90, this is 25, this is 6, oh sorry, there is a Ya here. So therefore exactly one customer is that, and then we can, right, pretty much do this painstakingly for Na equals 0, which we want to compute now. So therefore I can compute E of Na by simply so now I have the mean, but how do we get the variance of the number of jobs in a particular queue? I have the probability distribution, right. So variance I can compute simply by doing E of j squared, I can compute E of na squared, and then right. So we can, so if I want to know the variance of the and E of na squared is simple, I know the distribution, so this is simply j squared and so on. So this will work out to 1.13. So what is the probability that there is at least one customer in this queue and one customer in this queue? So at least one in queue A and at least one in queue B. So what is that? So what is the formula? Ya into Yb, this is divided by G of n up, yeah, into G n minus 2. This again you can go back to the table and verify, right. Look at all the cases where this condition is met, simply enumerate that, right, and you can get the value that you want. So we can now get all these probabilities. Now what is the average queue length, right. So yeah, what is the average queue length? So QA is equal to probability that n is greater than or equal to j, and that we know is, so this is basically j equals 1 to n so if to do this is best to write a program, but yeah, you can, this we already computed by the way, which is right, you can also do it this way, you can compute QB also the same way, and that turns out to be 0.911, right. So we computed Q of A or basically E of Na previously with Na equals 0, Na equals 1, 2, 3 and so on, but I can also get the same thing, right, in a different way. So after that this is fairly straightforward. If I give you a system and I tell you compute this exact values, won't be, it's not a big deal at all. So what is x now? Alpha into alpha was 0.78, Yeah, sometimes suspect the book's answers. Okay, so that's all. We can just run through this and then compute everything else that we want this way. So that's the idea. Okay. Questions on this part? Okay. So this is a more accurate way of getting what we want. So the next section, which is basically extending this to include delay centers also, section 35.4 on time sharing. Right. So extending this convolution algorithm that is a fairly straightforward extension. I will just say read. So only thing is the delay center is considered as another device. Why not, right? With why not as the parameter, right, as the demand for that. So you simply scale z by the same factor alpha, and that becomes your y naught. Then everything else is the same. So then you will have p n naught, right. So now you have some customers in the thinking state, which is n naught, and then the device queues n1 through n 1 through m. So this is same as before. Except so that is the only term. You have this n naught factorial in your denominator, which we did not have before, right. So when n naught equals 0, it automatically became 1. So that is the only extension. Okay, that is the end of chapter 35.
So if you have given z value,
Yes, I am just ignored that in the previous case. That so if z equals 0, yeah, then this would not have worked. Then y naught would have been 0, and then 0 to the power some. No, in that case I am just assuming. Okay, so what I said here is when z equals 0 is basically right. So this is, there is no terminals in the system. If you have terminals with where there is no, there is a delay center in the system, right. So there is no, so without delay center is what we are thinking. Okay. Done. Okay, so two big topics still remain. The other ones are after this chapter 36. There is no other chapter in the book beyond that. So we will go back to some earlier chapters which are not as heavy, little bit easier to deal with. Okay. So the remaining topics, this load dependent service center, that is one addition. Then this hierarchical decomposition, and I haven't finished those balanced job bounds. I said I will come back to that later. We had the simpler bounds first. So those are the three big topics left to be done.